So for the third learning module of this lecture, which get excited will be the second to last lecture of the course, I wanted to go over the parallel axis theorem and show how it can be applied in order to compute the moment of inertia of composite areas. And this is a problem, hopefully you'll get it during this class. You'll get to do an example at least on your final exam, but it is something you'll see again in your mechanics and materials course. The good news is, as long as you've just heard these terms before and whatnot, you'll see it's actually an incredibly simplistic calculation, and what you're really trying to get is the concept, even if you forget how to do it. So all that the parallel axis theorem is, so let me kind of set up the motivation. The book does a really poor job of letting you know why this is useful. So as you'd imagine, and we'll see it in a later slide, a lot of geometries that we deal with in our daily lives are going to be repeated. They're going to be either simple geometries or concatenations of simple geometries. So a lot of these calculations, we're not going to be integrating these weird power functions to the nth order like we did last time. They're going to be things that we can tabulate. But when you compute the moment of inertia, it's always referenced relative to a specific axis. And in your application, you might want to compute it relative to another axis. So we want to tabulate things, but we might not need the tabulated information exactly how it's presented. And what happens in your tabulated information regarding the moment of inertia of areas, as you'll see, it's typically presented relative to horizontal and vertical axes that pass through the centroid of the object. However, if you're interested in computing the moment of inertia of an axis that's parallel to the centroid axis, you can use it. You can do that using this formula. So look at these two formulas here. What this is showing you is if, for example, you had the moment of inertia about the x prime axis, which is a horizontal axis passing through the centroid, but you wanted to compute the moment of inertia instead about the x-axis, which in this case is a parallel axis that's separated from the centroid axis by some distance dy. You can take the value that you can probably look up from the table. So this is the moment of inertia about that centroid axis, and just adjust it by adding on whatever area you're trying to compute the moment of inertia about, plus the square of the separation distance between the axis of interest and the centroid axis. So this formula looks kind of funny, but when you apply it, you'll see it's actually not that bad. So they're showing it for this infinitesimal case and whatnot. But what usually happens in practice is this will be like a square, right? And you're trying to compute the moment of inertia about this axis. So you'll know the moment of inertia about the centroid, which will go right through the center of that square. You'll know the area of the square. So all you'll have to do is multiply the area times the square of this distance in between. So it's probably not an incredibly surprising formula to you. The distance separating the two axes is again squared, because remember the moment of inertia is the second moment, and the way that you compute the moment of this area is always to take a squared distance times an area. So not overly surprising to you, but I want to emphasize that the main reason that this is important is that you usually have these values here tabulated for simple shapes. So another concept that is introduced here in the text is the radius of gyration. When you get into kind of some of your more advanced mechanical engineering courses, you'll hear this concept. Again, it's a physical property of a shape that's useful, particularly in designing cylindrical columns in support structures. And it's just defined as the ratio of so it's defined relative to both traditional axes in a two-dimensional sense. So the radius of gyration is just defined as the square root of the moment of inertia relative to the area. So you have two, again, quantities, kx and ky. So not overly important here. Just remember when you hear these terms again down the road that it's a property of an area that's useful in actually designing support structures, much like the moment of inertia was. But you can kind of relate these two things to one another. If you square both sides, what you find is you can rewrite this as ix equals kx squared a. So you can kind of see that this kx, these radius of gyrations, kx and ky, they look like the distance terms in your original moment of inertia computations. So that's why they're called a radius of gyration, and that's why they have units of distance. So when you want to compute moments of inertia for composite areas, so the big motivation here is these cross sections of these beams, which is the main use of using moment of inertia, at least for everything that we've talked about so far in statics, is they can be viewed as a concatenation or a combination of very simplistic shapes for which you have the moments of inertia tabulated. So the moment of inertia is purely linear, meaning that if you want to find the total moment of inertia of an area, if you can break it into parts and find the individual moments of inertia, then you just add them up. Now, one of the things that you probably have some experience with, either from your prior physics course or approaching things like this, is oftentimes it's not that a shape is just a sum of two shapes. It's a sum of a shape and a simple shape cut out, or a hole. So for example, I did the idea of a donut earlier in the class when I was talking about determining how the centroid of an object isn't always on the physically on the area. You can view that as a big circle with a little circle cut out. So in that case, if you wanted to find the moment of inertia, you wouldn't add the moment of inertia of the big circle and the little circle. You would subtract the little circle from the big circle. So if it's a hole, just make sure you don't add it, you subtract it. So the way you do this is you just look at what you're trying to calculate the moment of inertia of, and you see, oh, I can break that down into a rectangle and a triangle and a circle. And basically what is going to govern what you're breaking it down to are the shapes you have available in this table in the back of your book that I'll show you a picture of in 2 slides from now, but I also uploaded it to the learning modules for this week. It may so happen, and will likely happen, that you'll want to find the moment of inertia not about the centroid of these shapes, but about some other axis. So just apply your parallel axis theorem, which basically means see the perpendicular distances that you need for your geometry and multiply by the square of those times the area to adjust the moments of inertia. And then just add them up, making sure that if it's a hole, that you subtract it away. So here's an example. What if we wanted to find the moment of inertia of this shaded area about both the, it looks like we only need to do it about the x-axis here, and we also want to find the radius of gyration, but remember, radius of gyration, we can get easy once we have the moment of inertia, just take the square root of moment of inertia divided by the area. So we're not going to be able to look up a shape like this in a table. It's kind of like got a rectangular part. It's got a little bit of a taper here on the end. It looks triangular. It's got a hole cut out that's a circle. But the question is, we can look up, and I'll kind of give you a spoiler alert, the moment of inertia of rectangles, circles, and triangles. So what this really boils down to is, can we decompose this into a sum or difference of simple shapes? And the answer is we can. Right? If we were to take a big rectangle, which we're denoting here by A, that's the entire big area on the outside, so 300 high millimeters, and what would that be, 350 millimeters wide, subtract away the circle and subtract away this triangle, that would give us the area. So all that we need to do is compute the moment of inertia of this big rectangle, compute the moment of inertia of the circle and the triangle, and subtract away the circle and the triangle's moment of inertias from the big rectangles. So the first thing you're going to have to ask yourself is, so all of these tables that we're given, right, they're going to have the moment of inertia about a horizontal axis that goes through the centroid. So for example, in the case of the big rectangle, right, the centroid would be located at 150 millimeters. So if I want to compute the moment of inertia about the x-axis in this case, since the centroid axis for the rectangle is 150 millimeters up, that's why they're saving this value here. Because remember, when we actually apply the parallel axis theorem, I hate to go all the way, I hate when people jump around on slides, but this is what this dy or dx dy in this case, because we're computing the moment of inertia about the x-axis. This is this quantity. It's just how far away is the axis of interest from the centroid axis. So for all of the little parts here, we need to know what the centroid axis is. So for the rectangle, it's simple because the axis of symmetry is right in the middle. It's also simple for the circle. That's why these two are the same. Circle has a horizontal line of symmetry right through the middle, so that's where its centroid is, and that's 150 millimeters away. Don't forget that for a triangle, it's basically either a third up from the fat part of the base or 2/3 the other way. So if this is total 300, and we'll go from the skinny end, that will be 2/3 up. That's going to be 200 millimeters. And just in case anyone is confused how that is, if you notice, we know that the centroid, so down from the wider end of the base, is 1/3 of the height. So another way to say that is from the skinnier end of the base, it's 2/3 away. So going back to this triangle here, it's going to be from this end 2/3 of this height. So if the height is 300, that is 200 millimeters. So these are just distances of each of these shapes from the axis, the horizontal axis of the centroid, which for the rectangle and circle are here, and for the triangle is here, to the axis about which we're computing the moment of inertia, and we need that for the parallel axis theorem. So where are they getting like these numbers from? So remember, they're calling A the rectangle. Well, if you go back and you look at this formula from your textbook, what you see is we can compute the moment of inertia about the horizontal axis through the centroid is 1/12 times the width of the rectangle times the height cubed. That's all that they're doing here. 1/12 times the width of the rectangle. And if I wish I had my dot cam. Unfortunately, I came home for the day, I guess at 10 o'clock. I thought it was time to head on out. But you kind of want to have little drawings of this. It'll make it a lot easier. Like have the rectangle in front of you, and you'll see the width is 350 and the height is 300. So that's where, and then you go to this formula, you say, okay, I need to multiply by the width, which was 350, and the height, which was 300. I need to cube that. That's where this 350 and 300 cubed is coming up. This is where the 1/12 is coming up. Now the question is, what's going on here, right? What is the 350 times 300 times 150? Well, remember 350 times 300 is just the area of that rectangle. So the parallel axis theorem says take the moment of inertia about the centroid axis and add on the area times the distance from the axis of interest to the centroid axis. So remember, for the rectangle, the centroid axis was 150 millimeters away from the x-axis. So that's what this is. This is just the a dy squared term. So this is just an example of the parallel axis theorem. In a similar fashion, we can go and look up for the circle. If we want to compute its moment of inertia about its horizontal axis, it's 1/4 pi r to the fourth. So the question is, just go back to your geometry and you notice the radius is 75 millimeters. That's where this 1/4 pi 75 to the fourth is coming from. And then don't forget, you need to add on your adjustment term, which is a times that perpendicular distance squared. For a circle, the area is pi r squared. That's what this is. And this is that dy for the circle that we've determined previously. Just crunch the math, and that's what you get. For the triangle, notice that about the centroid, the moment of inertia is 136, the base times the height cubed. So just go in your problem and notice that the base is 150, the height is 300. That's where this 150 times 300 cubed has come from. Remember that 136 was a constant of proportionality. And just adjust it by the parallel axis theorem. So the parallel axis theorem says take the area, which for a triangle is 1/2 base times height, and multiply by that perpendicular distance, which since the triangular had the triangle, not the triangular, has a centroid that was higher up than the other two. These were only 150 up. This was 200 up. That's why this number is larger. And don't forget, once you have these three quantities, since these are wholes, they have to be subtracted from the original moment of inertia, and that's how they're actually getting that quantity. So if I wanted to actually determine what the radius of gyration was, all that I need to do is take that moment of inertia that I computed and compute the area. And remember, this is a true area, meaning that holes have to be subtracted again. If you compute the area, you'll get this, and just plug and chug, and you find the radius of gyration of this shape to be 146 millimeters. So we only got one more learning module left where I'm going to set up the final problem, and it's going to be pretty similar to that last problem that we just did. So only about 5 more minutes of having to listen to me. That's a good thing. I'll see you in the next video.